Today, we'll solve LeetCode 110, Balanced Binary Tree. This is a classic recursion plus depth-first search problem that frequently appears in interviews to test whether you can combine multiple conditions in one traversal. If you understand this pattern, you'll also be comfortable with many other tree problems. We're given a binary tree. A binary tree is height balanced if, for every node, the height of the left subtree and the right subtree differs by, at most, 1. If this condition is violated anywhere in the tree, the answer is false. Otherwise, true. Let's walk through a few examples to make this concrete. Example 1. At the root node, the left subtree has height 1, and the right subtree has height 2. The difference is 1, which is allowed. Since every node satisfies the condition, the tree is balanced. The output is true. Example 2. Here, the left subtree keeps growing deeper and deeper. Some node, the height difference becomes greater than 1. Once that happens, the entire tree is considered unbalanced. The output is false. Example 3. The root is empty. An empty tree is trivially balanced because there are no nodes to violate the rule. The output is true. This is a depth-first search problem. Every node, we need 2 things. First, the height of the subtree. Second, whether the subtree is balanced. The trick is to combine both checks into one depth-first search traversal. Instead of checking balance separately, that's too slow. For large trees, here's the core idea. We use depth-first search. If a subtree is balanced, we return its height. If a subtree is unbalanced, we return -1. By -1, it acts as a signal. Once we detect an imbalance, we stop further computation. The signal propagates up the recursion, and the final answer becomes false. Now let's walk through the step-by-step logic. Each node, we do the following. Step 1. Recursively get the height of the left subtree. If it returns -1, immediately propagate -1. Step 2. Recursively get the height of the right subtree. If it returns -1, again propagate -1. Step 3. Check the height difference. If the absolute difference between left and right is greater than 1, return -1. Step 4. Otherwise return 1 plus the maximum of left and right. Finally, if the root returns -1, the tree is not balanced. Otherwise, is balanced. Now let's walk through the final solution. We define a helper function called height, which performs depth-first search. If the current node is null, we return 0. This represents the height of an empty subtree. Next, we recursively compute the height of the left subtree. If the left subtree returns -1, we immediately return -1. Then we recursively compute the height of the right subtree. If the right subtree returns -1, we again propagate -1. Now we check the height difference. If the absolute difference between left and right is greater than 1, the subtree is unbalanced, and we return -1. Otherwise, the subtree is balanced. We return 1 plus the maximum of the left and right heights. Finally, we call the height function on the root. If the result is not -1, the tree is balanced. Finally, let's discuss time and space complexity. The time complexity is O of n because each node is visited exactly once. The space complexity comes from the recursion stack, which depends on the tree height. In the worst case, the tree is skewed and space is O of n. For a balanced tree, the height is logarithmic, giving O of log n space. Before we finish, let's review common mistakes and edge cases. First, computing the height separately for each node is a common pitfall. Second, forgetting to short-circuit once an imbalance is found leads to unnecessary computation. Third, not handling an empty tree. Remember, an empty tree, where the root is none, is always balanced. Finally, the key optimization is early termination using -1. To summarize, this is a DFS plus recursion problem. The key pattern is returning extra information from recursion. Using a sentinel value, like -1, helps you optimize brute force into linear time. Here's an interview tip. Whenever a tree problem asks for height plus some condition, ask yourself, can I compute both in one DFS? That's the difference between a good solution and a great one.